So the kind of polynomial approximation we're doing, which is picking one particular point and trying to match the derivatives of the function at that point, is called a Taylor approximation or Taylor polynomial, and later we'll call it a Taylor series if we go on to infinity. Of course, like most mathematical discoveries, it's not named after its actual discoverer. Madhava in India discovered it 100 or more years before Taylor did in England. Let's keep going and talk about approximating cosine x at or near x equals 0. Why do I say at or near? Well, we do the computations of derivatives at x equals 0, but we want approximations for values near x equals 0. So let's make the same kind of table we did before. So we'll have our derivative number, which you could also call the order, the derivative formula, the derivative value at x equals 0, because that's what we said there, and then the polynomial term. So let's do zeroth derivative. What's the zeroth derivative of cosine? Cosine. And we'll fill in this column later. Let's just do the derivatives for now. What's the first derivative? It's what, negative sine. Second derivative is negative cosine. You don't actually have to write the f prime, f double prime if you don't want to. I'm just doing that for pedagogical purposes at this point. F triple prime would be derivative of negative cosine. Of cosine is negative sine, so we'd have minus minus. So we just have sine x. Fourth order, we'd have cosine x. And then what happens? It just repeats. Let's try it at least 2 more times. Derivative of cosine x is negative sine x, and then negative cosine x. What's the derivative value at x equals 0? So cosine of 0, cosine of 0 is not 0, it's 1. Sine of 0, negative sine of 0, is 0. Negative cosine of 0 is 1. Oh, with a negative, negative 1. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. And negative cosine 0 is negative 1. All right, and then let's go fill in the polynomial terms. How about this one? It would just be the 1. You could say 1 times 1 over 0 factorial times x to the 0, but we usually don't bother writing that. This one would be 0 times x. This would be negative 1 times x squared over 2 factorial. If you don't feel like writing a fraction like 1 over 2 factorial, you could write it this way. What I do not mean here is x to the 2 divided by 2 factorial. The dividing is happening after the squaring. And then 0 times x cubed over 3 factorial, 1 times x to the 4th over 4 factorial, 0 times x to the 5th over 5 factorial, and negative 1 times x to the 6th over 6 factorial. So you just add those all up, and that would be your 6th order polynomial approximation. That's right here. That we don't mean x to the 2 over 2 factorial like that. We really mean more like 1 over 2 factorial x squared. All right. So what happened here, something interesting, we didn't get all 1s like we got with e to the x, and every other term was a 0. Which terms were 0? The odd power terms. Let's write out the sum we got in a horizontal way like we're kind of used to. So 1 plus negative 1 x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we'll put an etc. there, like we could maybe keep going. We got only the even powers. 2, 4, 6. Oh, and a 0, right? 0 is an even number. And if you think about cosine, let's graph cosine real quick. That has what's called even symmetry, just like x squared has symmetry around the y-axis. X to the fourth has symmetry around the y-axis. So that all seems to make sense. We should go check it in Desmos though, right? So here we are, we've got cosine x here. Let's show the 0th order approximation. We remember we were approximating near x equals 0. So that seems to be a pretty good approximation right there, right? Let's do the first order. Well, that had a slope of 0, so that seems to be the same as the 0th order approximation. And then let's show the second order approximation. That does seem to capture that kind of downward parabola-like part of cosine right there. Then let's show the third order approximation. Well, again, that had a coefficient of 0, so that's the same as the second order approximation. And then we can show the fourth order approximation, and that now has a positive quartic aspect to it, so it ends up increasing in the long run over here and as we go back toward negative infinity, but it does stay closer to the original cosine curve than the second order approximation does. And then if we show the fifth order approximation, that's the same as the fourth order because it had a coefficient of 0, because we have no odd symmetry going on here. And then the sixth order stays even closer to the original function longer than the fourth order or the second order. So this does seem to be a good way of approximating cosine, and it gets better and better as we include more and more terms.